Good day, everyone. We are going to talk about the integrals of periodic functions. In our previous video, we talked about the analytic description of periodic function, and we also talk about sinusoidal and non-sinusoidal functions under Fourier series. So in today's video, we are going to talk about the integral of periodic function. So this integral of periodic function, they are just like standard integrals that will help us when we are finding the Fourier series coefficients. So I would like us to take up to 5 or more integrals so that if we come across such integrals when finding Fourier series coefficients, we are not going to stress ourselves to start integrating them. We can just substitute their values. So the first integral of periodic function I would like us to take is the integral from minus pi to pi of cos nx dx. The integral from minus pi to pi of cos nx dx. So let's integrate this function. Take note, this limit minus pi to pi is a single period. So we are integrating cos nx over a single period. Or another person can also decide to integrate from 0 to 2 pi instead of from minus pi to pi. It's still the same thing. So let's integrate this function and see what we have. So if we integrate this function, don't forget to integrate any trigonometric function. You first of all differentiate the angle and divide it by the derivative of that angle. So the angle here is nx. So if we should differentiate nx with respect to x, we are going to have n. So we are going to divide it by n, which is the derivative. So we have 1 over n, then into, we are going to integrate the function now. And if we should integrate cos, you have sine. So if we integrate cos nx, we have sine nx. Then don't forget to take your limit from minus pi to pi. From minus pi to pi. So this implies that we are going to have 1 over n into, don't forget to substitute your upper and lower limits. Substituting your upper limit, you have sine n pi, then minus, you substitute your lower limit, sine minus n pi. This is what we have. So this implies that we are going to have sine pi. Sine pi is 180. Sine pi is 180, and sine 180 is 0. Also here we have minus n pi. If you should do sine minus 180, you will still get 0. So sine n pi is 0. So we are going to have 1 over n into 0 minus sine minus n pi, which is sine minus 180, is still 0 minus 0. So this will give us 1 over n into 0, which is equal to 0. So therefore, the integral from minus pi to pi of cos nx dx is equal to 0. So I'd like us to take the second one. The second one there is the integral from minus pi to pi of sine nx dx. The integral from minus pi to pi of sine nx dx. And this will give us, following the same process, you first of all differentiate the angle. We have 1 over n into, you integrate the function. If you should integrate sine nx, you have minus cos nx. Take note, if you integrate cos, you have sine. If you integrate sine, you have minus cos. So we have minus cos nx. You take your limit from minus pi to pi. And of course, this will give us, we have minus here, so we can bring out the minus. Minus 1 over n into cos nx from minus pi to pi. So this is what we have. So this implies that we are going to have 1 over n into 1 over n into cos n pi, cos n pi. Then you substitute your lower limit minus cos n into minus pi. So this is what we have. So this implies that we are going to have this is minus 1 over n into cos n pi. Please take note, cos is an even function. So if you should take the negative of cosine, you will still have the positive. That is, if you have cos minus 180, it's the same thing as cos 180. Or if you have cos minus 90, it's the same thing as cos 90. Please take note, for cos, it's the same thing. So this implies that we are going to have cos n, because this will change to positive, cos n pi. And this means that we have minus 1 over n into cos n pi minus cos n pi is 0, which is equal to 0. So therefore, the integral from minus pi to pi of sine nx dx is equal to 0. So this is what we have. So I'd like us to take the third one. The third one there is the integral from minus pi to pi of cos square nx dx. The integral from minus pi to pi of cos square nx dx. But before we start integrating for cos square nx dx, I want us to establish a relationship between the cosine of double angle. Please take note, from the cosine of double angle, from the cosine of double angle, from the cosine of double angle, we have cos 2 pi is equal to, from the cosine of double angle, we have cos 2 pi is equal to cos square pi minus sine square pi. Please take note, the cosine of double angle. So since we are looking for cos square nx, we can still rewrite this cosine of double angle in terms of nx. So we can rewrite it as cos square nx is equal to, cos 2nx, cos 2nx is equal to cos square nx minus sine square nx. And if you observe, what we are looking for here is cos square nx. So we can make cos square nx subject to formula. But first, before we make cos square nx subject to formula, we need to express sine square nx in terms of cosine. And don't forget that cos square nx plus sine square nx is equal to 1. So we can make sine square nx subject to formula from here. So this implies that sine square nx will be equal to 1 minus cos square nx. So this is what we have. So we can substitute for sine square nx here. So by substituting, we are going to have cos 2nx is equal to cos square nx minus sine square nx is 1 minus cos square nx. 1 minus cos square nx. So this is what we have. So this means that we have cos 2nx is equal to cos square nx minus 1 minus times minus plus cos square nx. So we have cos square nx here, we have cos square nx here. We can collect like terms and add them up. So we have cos 2nx is equal to cos square nx plus cos square nx will give us 2 cos square nx minus 1. But don't forget, we are looking for cos square nx. So from here, we can make cos square nx subject of formula. So we have 2 cos square nx minus 1 should come over here. We have this is equal to cos 2nx plus 1. So if you divide both sides by 2, you have cos square nx is equal to 1 over 2 into cos 2nx plus 1. So this is what we have. So in place of cos square nx, we are going to substitute 1 over 2 cos 2nx plus 1. So let's do that over here. So we are going to have the integral from minus pi to pi into, we have 1 over 2, 1 over 2 cos 2nx plus 1. So this is what we have. But don't forget, 1 over 2 is a constant, so we can factor out 1 over 2. So this implies that we are going to have 1 over 2, the integral from minus pi to pi of cos 2nx, cos 2nx, cos 2nx plus 1, all with respect to x. Please take note, with respect to x. So let's integrate this function. We are going to have 1 over 2 into, if you should integrate cos 2nx, don't forget, first of all, differentiate the angle 2nx. If you should differentiate 2nx with respect to x, you have 2n, and then you divide it by that derivative. So this implies that we are going to have 1 over 2, 1 over 2n into, if you should integrate cos, you have sine. So we have sine 2nx. This is what we have. Then also, if you should integrate 1 with respect to x, you just have x. And don't forget to take your limit from minus pi to pi. All right, let's continue. All right, so here we have 1 over 2, 1 over 2 into 1 over 2 into 1 over 2n, 1 over 2n into, if you should take your limit from minus pi to pi, from minus pi to pi of sine 2nx, you have sine 2n pi, because you are substituting pi for x. So we have sine 2n pi, then minus sine 2n into minus pi. So this is what we have. Then also, the next one here we have is x plus, you substitute pi for x now, plus pi. Then the lower limit there is minus pi. You close your bracket. So this is what we have. So this implies that we are going to have 1 over 2 into 1 over 2n. Please, sorry, for our limit, please take note, for our limit, we are substituting x for pi, so we have pi. But don't forget, from the upper limit to the lower limit is minus bracket, then you substitute your lower limit, minus pi. So this is what we have. So we have 1 over 2n into, don't forget, we said sine 180 is always 0. Please take note, sine 180 is always 0. No matter the multiple, even if here is to be 20 or here is 30, sine 180 is always 0. Please take note. So we have 0 minus. Also, we are still going to have 0 here. Sine 180 is always 0. Even if here is minus, you still get 0. Minus 0 plus pi, minus times minus plus pi. So this is what we have. So we have 1 over 2 into 0 minus 0 is 0. 0 times 1 over 2n is 0. So pi plus pi is 2 pi. So you see, 2 we cancel 2. So we have pi. So therefore, the integral from minus pi to pi of cos square nx dx is equal to pi. Please take note of these integrals of periodic functions because we are going to be using them in finding the Fourier series coefficients. Now the fourth one we have the integral from minus pi to pi of, this was cos square nx dx. So the next one here will be sine square nx dx. So we have the integral from minus pi to pi of sine square nx dx. But don't forget, we said that from the cosine of double angle, we have cos 2nx is equal to cos square nx minus sine square nx. So this is what we have. For cos, we express the cosine of double angle in terms of cos. So for sine, we are also going to express it in terms of sine. But don't forget that cos square nx is the same thing as 1 minus sine square nx, because cos square nx plus sine square nx is equal to 1. So if you should make sine square nx subject, cos square nx subject of formula, you have 1 minus sine square nx. So this means that we have cos 2nx to be equal to 1 minus sine square nx minus sine square nx. So this means that cos 2nx will be equal to minus sine square nx minus sine square nx will give us minus 2 sine square nx. So let's make sine square nx subject of formula. We have minus 2 sine square nx is equal to cos 2nx minus 1. So divide both sides by minus 2. You have sine square nx is equal to, divide both sides by minus 2. You have minus 1 over 2 into cos 2nx minus 1. So expand this, you have sine square nx to be equal to 1 over 2 into, this become minus, this become plus, 1 minus cos 2nx. So this is what we have. So instead of integrating sine square nx, we can just go ahead and integrate 1 over 2 into 1 minus cos 2nx. So in place of sine square nx, we are going to substitute 1 over 2 into 1 minus cos square nx, because we cannot integrate sine square nx direct. All right, so I'll be cleaning this part. So this implies that in place of sine square nx, we are going to integrate from minus pi to pi of 1 over 2 into 1 minus cos 2nx dx. So this is what we have. And of course, 1 over 2 is a constant. So we have this is equal to 1 over 2, the integral from minus pi to pi of 1 minus cos 2nx dx. So if we should integrate 1 with respect to x, we have x. So we are going to have 1 over 2 into, if you integrate 1, you have x minus, to integrate cos, you first of all differentiate the angle. If you differentiate 2nx, you have 2n. You divide it by that derivative. So we have 1 over 2n, 1 over 2n into, if you should integrate cos now, you have sine. So we have multiplied by sine 2nx. So this is what we have. Don't forget, we take our limit from minus pi to pi. So let's quickly take our limits. We have 1 over 2 into, if you should substitute x for pi, you have pi. But don't forget, from the upper limit to the lower limit, you need to attach minus. Then the lower limit there is minus pi. Minus pi. Then we have minus 1 over 2n into, you substitute for sine, you have sine 2n pi. So we have sine 2n pi, sine 2n pi. Then also for the lower limit, you attach minus sine 2n minus pi. So this is what we have. So this implies that we are going to have 1 over 2 into pi plus pi will give us 2 pi. 2 pi minus 1 over 2n into, we said sine 2n pi is always 0. Sine pi is always 0. No matter the multiple, we are still going to have 0. So this is 0 minus, also we have 0. So this means that we are going to have 1 over 2 into 2 pi. So 2 we cancel 2, we have pi. So therefore, the integral from minus pi to pi of sine square nx dx is equal to pi. Please take note of this integral of periodic function. We are going to be using them in finding the Fourier series coefficient. So the fifth one I would like us to take there is the integral from minus pi to pi of cos nx sine nx dx. Please, without wasting much time, this will give us 0. Please take note, it will give us 0 without wasting much time, because we have so many to integrate. This will give us 0. And also, the sixth one there is the integral from minus pi to pi of cos nx sine mx dx. Observe carefully, we have cos nx sine mx. What the difference is just m. Here we have m and here we have m. In case the angle of sine is different from the angle of cos. Here it means that the angle for sine will be the same. If this angle here is 180, here also will be 180. But for this one, if the angle is 180, here can be 360. But of course, this will still give us 0. It will still give us 0, actually. So the integral of cos nx sine nx dx is 0. The integral of cos nx sine nx dx is 0. Now, what about the integral from minus pi to pi of cos nx cos mx dx? The integral of cos nx cos mx dx. Let's see what we are going to have. This will give us, see, it will give us 0 if n is not equal to m. This will give us 0 if n is not equal to m, because if n is not equal to m, we are going to have different angles. So this will give us 0. But if n is equal to n, we are going to have pi if n is equal to m. Because if n is equal to m, we have cos mx, which will give us cos square mx. And we have seen that cos square mx is equal to pi, or cos square nx is equal to pi. So this will give us pi if n is equal to m. So let's take the next one we have there is the integral going from minus pi to pi of sin nx sin mx dx. And this will give us 0 if n is not equal to m. And this will also give us pi if n is equal to m. Because we have seen that if n is equal to m, we have sin nx, which is sin square nx. And we have seen that sin square nx dx is equal to pi. So this implies that we are going to have pi if n is equal to m. So these are the integrals of periodic function we are going to be using in finding the Fourier series coefficients. Please take note of these 8 standard integrals. Please check on for the next video for the Fourier series coefficients, so we can start solving problems on Fourier series. Thank you for watching this video. See you in the next video.